Welcome to Smart Bites Tech and Science.
Great to be here.
Today we're diving deep into something pretty exciting in quantum computing.
Uh-huh.
You flagged a development about a new superconducting quantum computer. And, well, we really want to unpack why it's significant.
Exactly. We're talking about Fujitsu and Riken over in Japan.
Right.
They've just announced a new 256-Qubit Superconducting quantum computer.
Okay, 256. That follows their earlier 64-qubit system, doesn't it?
It does. And understanding why this jump matters and what it might unlock, that's the mission today.
Perfect. So 256 qubits, that's 4 times the previous 64. Now, just a level set for everyone, maybe a quick refresher. What exactly is a qubit and why is having more just, well, better?
Sure. So think of your normal computer bit. It's either a 0 or 1, like a light switch being on or off.
Simple enough.
A qubit, though, because of quantum mechanics, it can be a 0, a 1, or kind of both at the same time.
That's the superposition thing.
That's superposition, exactly. And this both at once ability means a quantum computer can explore just a huge number of possibilities all at once.
Way more than a classical computer could handle for certain problems.
Precisely. So going from 64 to 256 isn't just adding 4 times the switches. It's an exponential boost in that parallel processing power.
Right. It scales much faster. And the announcement positioned this as, I think, world-leading for superconducting qubits.
That's the claim, yes. It definitely puts them right at the forefront of this specific technology.
And it's not out of the blue, is it?
Yeah.
You mentioned the 64-qubit machine?
No, not at all. That one launched back in October 2023.
Okay.
And it had support from MEXT, the Japanese Ministry of Education, Culture, Sports, Science, and Technology.
Government backing.
Right, under their QLEAP program. So it shows a clear funded progression. This 256-qubit system is the next logical step in their roadmap.
So it feels like the focus is really shifting now. Not just bigger qubit numbers, but getting these things to do useful stuff, practical application.
Exactly. That's the key phrase here. Practical application.
So what kind of problems become, more solvable with 256 qubits? What does this actually let us do?
Well, this is where it gets really interesting for you listening. We're getting closer to tackling problems that are just, well, impossible for today's best supercomputers.
Like what, for example?
They specifically mention analyzing larger, more complex molecules.
Okay, so maybe drug discovery, designing new materials.
Precisely those kinds of things. Understanding how molecules interact is fundamental there. Also, crucially, more qubits are vital for better error correction.
Error correction. Because quantum states are super sensitive.
They're incredibly fragile. So having more qubits allows you to build in redundancy, check for errors, and ultimately build more reliable quantum computers. You need that fault tolerance.
Makes sense. It's like having backups for your delicate quantum calculations. Now, they talked about a scalable 3D connection structure. That sounds clever. What's the idea there?
Yeah, it is quite innovative. So imagine you have basic building blocks, units of 4 qubits each.
Okay.
Instead of just laying them out flat, like on a 2D chip, they're arranging them in 3 dimensions, stacking them, essentially.
Like building upwards.
Kind of, yeah. This allows for, well, much denser packing and more efficient connections between all the qubits as you scale up. You avoid some of the wiring traffic jams you get in 2D.
Right, you run out of space for wires on a flat surface.
Exactly. And what's really key here is that this new 256-qubit machine, it uses the exact same 4-qubit unit cell design as the 64-qubit one.
Oh, interesting. So it proves the concept scales.
It really does. It shows their architecture is genuinely scalable. They can just, replicate and stack these units without a massive redesign each time.
A bit like building with standardized Lego bricks, but in 3D. That sounds much more sustainable for getting to even higher qubit counts.
That's a good analogy, yes.
Okay, another engineering point they made was quadrupling the density inside the same cooling unit, the dilution refrigerator, that they use for 64 qubits. How hard is that?
Oh, that's a serious achievement. These machines, as you know, need to be incredibly cold, just fractions of a degree above absolute zero.
Right, using those big dilution fridges.
Exactly. So fitting 4 times the qubits, plus all the control wiring and components into the same physical volume while maintaining those extreme temperatures and the necessary vacuum. It's a huge engineering challenge.
Wow.
It shows real progress in integration and managing the physical infrastructure needed. Making things more compact is crucial for practicality.
Definitely impressive.
Yep.
More power, same space, same extreme cold.
Okay.
Okay, now, they mentioned integrating this into their platform for hybrid quantum computing lineup.
Yeah.
What does hybrid mean here?
Right. Hybrid computing is becoming a really important concept. Basically, it means combining quantum computers and classical computers, letting each do what it does best.
Ah, so not quantum replacing classical, but them working together.
Precisely. Many complex problems have parts that are perfect for a quantum approach and other parts that are still faster or easier on a regular supercomputer. So, a hybrid platform aims to manage that workflow seamlessly. It lets you use both types of processing power efficiently for a single problem.
Makes sense. Get the best of both worlds. And it sounds like they're making this accessible fairly soon.
Yes, that's a key takeaway. They plan to offer this hybrid platform, including access to the new 256-qubit machine, to companies and research institutions globally,
When's that planned for?
starting in the first quarter of fiscal year 2025. So, not far off at all.
That really is just around the corner. It signals a move towards wider use.
It absolutely does.
Yeah.
It's about democratizing access, moving beyond purely internal R&D.
And looking further ahead, they seem pretty ambitious.
Oh, definitely. Fujitsu and Riken are clearly committed to pushing this forward, on both the hardware side, like this chip, and the software and algorithms needed to actually use it effectively.
Any specific next steps mentioned?
Yes. They've stated a goal to launch a 1,000-qubit computer.
Wow, 1,000.
Yeah. In 2026, plan for a new building at Fujitsu Technology Park.
That's a rapid timescale.
It is. And reinforcing that long-term view, their joint Riken RQC Fujitsu Collaboration Center, that partnership has been extended out to March 2029.
So they're in this for the long haul, clearly focused on building even bigger machines.
That's the strong impression, yes. Sustained R&D for the future.
Okay, so just to kind of wrap up the core achievement here, it's this new 256-qubit chip from Fujitsu and Riken.
Right.
Significant not just for the number, but the clever 3D architecture that scales, the engineering feat of density in the same cooler,
Uh-huh.
and its planned integration into a hybrid platform becoming available globally quite soon, all built on that ongoing collaboration.
You've got it. It's progress on multiple fronts, showing the technology is really maturing.
So thinking about the bigger picture, what does this mean for you, the listener? Well, this kind of jump in qubit power brings us genuinely closer to using quantum mechanics to solve problems we just, well, couldn't solve before.
Absolutely. Things like designing revolutionary new materials, creating much more effective medicines, maybe transforming fields like finance or AI. The potential is enormous.
And it feels like it's becoming less theoretical and more tangible with each step like this.
It really does. This development out of Japan highlights the fast pace globally and, importantly, the effort to make these powerful tools accessible to more researchers and industries through things like their hybrid platform.
Definitely exciting times. We hope this deep dive gave you a clearer picture of this latest step forward. It certainly raises questions, doesn't it?
It does.
What possibilities does this open up in your mind? What huge challenges currently out of reach do you think this kind of quantum power might eventually help us conquer? Something to ponder for